this one is.
All right, so let's go ahead and get started. First of all, Happy New Year. Lunar New Year. Lunar, because it's actually the calendar is used by multiple countries. So more politically correct, it should be called the Lunar New Year. And can anyone tell me what year it is? Which animal? Which zodiac?
Pony.
Yep, wooden horse to be exact. Okay, so there's always an element associated with the animal. And next year is the year of the wooden horse. And it has already happened, okay, in China and all the other regions around there, it has happened already. So there are fireworks and whatnot, the celebration has started already. And of course here, nobody knows. So anyway, congratulations that you survived another year. I think that was the original intent of the celebration, because winter is harsh, okay? There's no food, it's cold, and many people die in the winter. So if you can survive, all the way to spring, so, it's time to celebrate. It's like, wow, you actually survived, and so did I. So that's what it is. The other thing, just point out little things that I have changed these days. On the Power Server, some of you know the Power Server. I added, a WordPress link to it, and have been busy writing certain things, about stuff that I found, and from Slashdot and other sources too. This one is kind of interesting. A company in Massachusetts is actually trying to do digital afterlife. In other words, if people die, after people die, they would go through all the log, all the email, all the chatting and whatnot of that person, and try to recreate that person so that descendants or friends and loved ones can continue to think, hey, that person has not died. I can actually chat with that person or text that person, and there will be a reply coming back that is modeled after that person's historical data of all the chat history and whatnot. It's well, if you read what I have to say about this, if you scroll all the way to the bottom, this is the result. Okay, and if you don't know what I'm referring to, you have to watch Caprica. Okay, the series Caprica, and then you will start to understand why I have this picture, in this little article. For those of you who are gamers, I have some other stuff too. This one is about Steam. So some of you are gamers, right? I mean, you play games and you know what Steam is. Steam has been working on Steam OS, Steam operating system, for a while already. And what it is Linux-based, but on top of Linux, they're trying to implement, quote-unquote, their own operating system. And not only are they, considering having their own operating system, kind of like Android, Linux-based, but on top of that, they have some customization. Steam is also it's going to be released later this year. Steam Machine, Steam Box. Okay. So I think they're trying to compete with Xbox and also PSPs. So it's interesting. Okay, we have a new player in a really, really highly contended, field already, and this is the only product that is Linux-based. What operating system do PlayStations use? Is it their own operating system?
Yeah.
Is it a BSD-based? Is it a Unix-based operating system, or is it completely proprietary and nobody knows what it is? Completely proprietary? Okay. So this is all interesting. Steam is big. I mean, the gaming industry is bigger than the movie industry now, and it's outpacing the movie industry at an accelerated rate. Okay, I think in 10 or 20 years, when you say let's go and watch a movie, it's almost like I tell you to listen to a radio show. It's like, okay, I'll try to dig up my my DVD player or something, right? I mean, nobody's going to have a DVD player in a year, let alone 5 or 10 years. So there are little things that I have written.
Just like only a few people have VHS players now.
Or beta.
Or beta. Yes.
Yep. Good memories, yes. All right, so let's go to this class. I found a few resources for this class. There's one thing that you might find useful. It's completely optional. You don't have to get it. But I found this when I was revising the curriculum of this class. This is going to be the last year that I'll be using the current curriculum, which I don't really teach to anyway. This is a really good book. I read through some portions of it, kind of glanced through the table of content, and I was telling myself, if I had 25 years to work on a textbook for this class, that's how it would look like. So there it is. And it's not even expensive. If you get the e-version, it's $11. It's a PDF file, with no DRM. Okay, I do not encourage anyone to kind of copy the file, even though technically you can, because the guy putting the PDF file out here, without DRM, because he just thinks DRM is ridiculous. It's also senseless to cost $100 for a textbook, with your other classes. So if you are going to use this textbook, I think $11 is not too much to ask. I have no affiliation with this guy. I'm not getting any kickback. I just thought with this kind of textbook, well thought out, well written, the author deserves some money, and $11 is not too much. The nice thing about this textbook is it is using the same architecture that we are using in this class. So the instruction set will be almost identical to what we talked about in this class. I think he's going to use the 64-bit instructions, and I'm using the 32-bit. But for the most part, it's going to be about the same. Okay, instead of move L for long for 4 bytes, it's going to be move Q for quad 64-bit. He's also teaching this class out of Linux. So a lot of the commands that we use in this class, I'm pretty sure he's going to use those commands as well. The book does cover more stuff than we will cover in this class, so it's not exactly matching what I will be teaching in this class. But I think it's a good reference material. So when it comes to the point where you think, well, text stuff is too terse, or I need something else to explain the concepts, consider getting this particular book, because I think it's a good complement to what I have already written for this class. Okay. Any questions about this? Can anyone guess? Let me see. It's not shown here. That's good. Okay. So can anyone guess when was the last time this book was revised? Because you know that certain books are revised more often than other types of books. Assembly language programming is one of those things where I could have written something 10 years ago, and it will still be exactly the same today. So when do you think was the last time this book was edited? No.
1989.
It was December 24th, 2013, last Christmas Eve. Yep. So we are talking about less than a month. Okay, a little more than a month. Okay, but it's really fresh. Okay. So I would definitely recommend you guys to take a look at it. If you go to the website, you can even download a preview of the book. It includes the first 4 or 6 chapters.
First 6 chapters, and then chapter 10 and 11.
Yeah, so you can definitely take a look and see if the content is is something that you expect for $11. How expensive are your other books? Like for $4.40 or something like that?
About the same.
Sorry? Free.
Free.
Oh, Mr. Fox is using his own material too. Yeah, I think that's a trend now. More and more people are doing that sort of thing, which I think is good, but the publishers do not like it. All right, so that's one. And what we'll do, or what I will do, is I will talk about the homework assignment first. I did promise you that we'll have a homework assignment today. It's called environment. It's the same way as it was last year for the most part. And this year I have just highlighted the commands a little bit more so that you know which part is a command and which part is not. So I would just ask you to read and do this whole thing and turn it in. It shouldn't take you too long once you know how to run a Linux system, whichever way you choose to do it. If you are running Linux natively on the computer already, you're pretty much all set already. If you use Windows for the most part, or you have to go from one machine to the next to do your homework assignment, you can also use the virtual machine. Okay? To install the virtual machine, I noticed that I forgot to mention where do you get VMware. So VMware is its own company, has its own website. So you go to the VMware website, you go to downloads, and it's a free product. So you just look for player, and here we have VMware player. Click download product, get it installed, and that should get the get the ball rolling. Okay. Are there any other questions? Go ahead.
Yeah,
Absolutely. Yep. Because I have gone through this, twice already in the lab, so I'm pretty sure the product works, and the file that I have linked on my website also works. Go ahead.
With VMware, can you have 2 sessions, or can you only have 1?
That's a good question. The way to do it, if you want to have multiple sessions or multiple students, is to enable bridge mode networking. So that way the virtual machine will have its own IP address, and once it has its own IP address, then you can just use a PuTTY or an SCP to connect to that particular IP address. But you will have to enable bridge mode networking, which may or may not be a good idea, because that means your virtual machine will be exposed to the rest of the network as the host. Any other questions? Yep.
I got two. So I was messing with VMware and I kind of got stuck in it. So I didn't know how to get out. Like I know it showed me, but I couldn't see it. Like I was like, how do you exit? And I try to exit and then exit me out of the actual user. So how do you get out?
You have to change to the root account and then use the command power off. Yeah, it's all written in the homework assignment too. Yep. All right, so you do have your homework assignment. You have 1 week to do it. I really don't think it will take you guys a week to do it, but I'm going to give you guys a week to do it. And you have to make sure that you turn it in using the command here. So there's a command that you have to run once you have your homework assignment done. And what it does is it creates a tar file, an archive file, that you will be uploading to the Moodle interface. And I will be downloading all of this stuff as one huge zip file that contains all the archives. My script will expand these archive files into their original folders and files, and then I'll have a script to automatically grade all the homework assignments. Well, as much as I can in an automated way. So that means you have to kind of read through this stuff carefully and make sure that you follow these rules, because my script is going to be kind of specific. Okay, it will be looking for certain things, so you have to follow the conventions as closely as possible. Okay? If it does say something about how to do something, you have to do it that way in order for my script to do it. Okay. Are there any questions? Now, since it's a week from today, that means if you run into any problems doing the homework assignment, you can still bring up the questions on Tuesday. Or I personally would recommend you to go to the lab and try to do it tonight. Okay, get it done, get it over with. It shouldn't take you a whole lot of time, and then then you don't have to worry about it. Are there any questions about this homework assignment? Go ahead. Say again? I cannot hear you.
Did you change something on the assignment, or was it the same one? It was in there last week.
It's the same one as last week. I just changed the highlighting a little bit, changed the font a little bit. But as far as what you're turning in, it's the same specification as last week. So if you have done it already and turned it in already, the one that you turning in from last week is going to work. Okay. All right. Any other questions? If there are no other questions, there's one more resource that I want to point out. It's really kind of cool too. It's a little bit too early to really use it in this class. Well, a little bit too early, meaning maybe half a class too early. Okay, we might be able to get to it today, if not next Tuesday for sure. It's called a von Neumann machine simulator. In other words, a von Neumann architecture is basically all of the processors today are following this particular model. So I'll explain that later. But this simulator is kind of fun too, because it allows you to go through a simulator and actually see how a von Neumann architecture works, step by step, and it allows you to specify your own microcode and also your own instructions. So it's really kind of cool. To write a program, using this simulator, you would have to go through the process of writing machine code, which is basically what computer scientists or early computer programmers have to go through when they write a program. Okay? You don't have an assembler, you don't have a compiler. You have to specify the exact words, the exact values to specify the operations. So it's a really kind of cool thing. We will get to that part, as at some point. And I was able to run it under Wine. Using Wine, I can run Windows executables, and this one worked just fine using Wine. So we'll take a look at that one, when it's time to do it. All right. So now we have most of the new stuff, taken care of, and I have a new roll sheet for this class with 60+ students enrolled. Sorry? No. Well, it's. We'll see. We'll see what happens, in this semester, because I think this is probably a record for this class. So go ahead and just initial your name next to today's column and pass it along. All right. So what we'll do is we are going to start with. Let's see here. Where am I here? We're pretty much done with the Linux topics, so we'll go ahead and start with. Well, I'll go ahead and start with binary numbers. Okay, some of these topics, we can start with one or the other. It doesn't really matter. Okay. So we're going to start with binary numbers. How many people already have the exposure of how to do conversions between binary numbers to decimal and that? I'm seeing about maybe 1/3 or 1/4 of the class. So the majority of the class seems not either too shy to raise the hand or not have the exposure of base conversion or dealing with binary numbers. Of those of you who do not know how to deal with binary numbers, I take it back. For those of you who know how to deal with binary numbers, do you prefer binary numbers to decimal numbers?
No.
Well, that's all I need with binary numbers, right? Just one finger. Okay. And I will point out, things that are really advantageous to binary numbers. Not only that you only need one finger, but you also have a very small multiplication table. Okay, so we'll get to that point. We'll talk about that too. Okay, first of all, binary numbers or dealing with values represented in different bases is easy. It's easy sneezy. Okay, if you know how to give someone the correct change, working as a clerk or a person working in McDonald's, you know how to deal with far more complex stuff than base conversion already. So what we'll do is we'll take a look at our U.S. currency, or at least the most common values that we use on a daily basis. So for that purpose, I'm just going to use mousepad, which is kind of like a notepad, as a whiteboard. So this way it is also captured. Okay. So let's say we start with the smallest unit, which is 0.01 of a dollar, a cent, right? The next one up is a nickel, a dime, a quarter, and I know we have half dollars, but those are fairly uncommon, so we'll move on to a dollar. I know we have $2 bills, and once again, they are fairly uncommon, so we'll move up to $5 bills, $10 bills, $20 bills, $50 bills, $100 bills, and I'll just stop there because these will be the most common values that we use in currency. Do you see any particular patterns or anything that is even repeating? Any repeating patterns as to the multiplier to go from one to the next?
5.
But it's not repeating, right? I mean, the 1 to 5, 5 to 10 is okay. So we are if you look at the multiplier in each step, we have a multiply by 5 here, multiply by 2 here, and then we have a 2.5. And then we have a 4, so far nothing in common. And then we have a 5 again, a 2 again, and now we have another 2 instead of a 2.5. And then we have a 2.5 here, and then we have a 4. It's all over the place. And yet, you have no trouble to tell me what is how to give someone the change using the least number of points and bills. Okay, let's kind of go through that exercise. I know I'm being silly here because you guys already know how to do this. So let's think about what you have to do to give somebody a change of, let's say $31.67. Okay, that's the amount of change. You cannot give the other person 3,167 cents because that's the easiest way to do it, right? From the calculation perspective. So what do? Okay, so let's say you have bills and coins of every single denomination. Okay, so you have all of these bills available to you. What are you going to do? You start with a $20 bill, a $10 bill, a $1 bill, and then you have 2 quarters. And then what?
A dime, a nickel.
A dime, a nickel, and 2 pennies. Okay. There we go. Did I miss something?
Your dime's off.
My dime is off. Okay.
That's fine. 0.05. Nickel is off.
Then my nickel is off. Oh, right. Okay, one more decimal. There we go. Okay. So apparently I cannot work at the McDonald's. Yeah. I just have to be better than the rest to stay there, right? They cannot fire everybody. So as long as you guys do not compete for the same job as mine, I'll be safe. All right. This is far more complex than base conversion. Okay? Because what you have to think about when you're dealing with base conversion is to think, well, what are our basic values? Okay? On the unit side, you have 1, 2, 4, 8, 16, 32. I'm pretty sure most of you are seeing the pattern here. Okay? It's just doubling the one before. But you can also go in the opposite direction. 0.5, 0.25, 0.125, and so on, having the value going in the opposite direction. Is that making any sense? So imagine our currency system is not the crazy way that it is. Instead, it is much more structured and much more orderly. Everything is just doubling the previous value. Is that making any sense so far? Okay. So let's see if we can use this new currency system to give somebody a change. So in this case, let's say it's $31.675 cents. Okay, because the other values won't work out, so we have to do it this way. Okay, so that's my change. What are you going to do with this? We don't want to start with 32 because the change is only 31 something. So you have to use the largest bill value that is lower than or equal to this value, to this number, right? It's 16. But how many of the $16 bills do I need? 1. Will I ever need to use more than 1 of any particular type of coins or bills? No. In other words, you don't have to do division. It's just comparison. You compare the amount of change to a particular currency denomination. If it's less than or greater than or equal to, then you just have to do it one way or the other. There's no division involved. Okay? So that's nice. Okay, so you have $16 and then what else?
Plus 841.
Plus 8, because the remaining portion is $15 and something, so you take an 8. And then after the 8, you have $7 and something, so you take a 4. And then after that, you have a 3 something. So you have a 2, and then you have a 1. So that would take care of the 31, right? 16 plus 8 plus 4 plus 2 plus 1 is exactly 31. So now we have the $0.675 to take care of. Well, we look into the fractional part. The largest one is a 0.5, so we can take one of those. And then once the 0.5 is taken care of, we only have
175.
0.175. It doesn't work out. Okay, we'll dock to the question instead. There we go. Okay, but the process, but you understand the process, right? Is a lot easier than dealing with the currency system that we actually use. Is that making any sense so far? Binary conversion. I don't see any binary numbers. Do you? Yeah, there's a binary number here. Because it is really just saying, do we have a one of $16 bills? Okay, let's start with 32, okay? We have 0 $32 bills, 1 16, 1 8, 1 4, 1 2, 1 1. We have 1/2, but we have 0 quarters, and then we have 1/8. That is the binary representation of this value. 31.625 is a base 10 representation of a particular value. But that same value can be represented using any base. You can use a base 3 number if you want. It works the same way. You can use a base 5 number if you want to use your base 5. So the basis that we're choosing is really just changing the way we represent a number. It's really just the name of the value, but it's not the only way to represent a number or the value that we're trying to represent. Are we doing okay so far with this number, the binary representation? The conversion to binary. Right. So binary numbers are kind of cool because it's actually not as difficult as we thought it is. Now, if you look at my slide, it's really just saying that it's reminding us what numbers really are and how to read the numbers. It's pointing out the obvious. Okay, with a base 10 number, 1,742. You basically write it out as 1,000 plus 700 plus 40 plus 2. Really obvious stuff, elementary school students can do it. And then you move it one more step and say, well, that means we have 1 of 1,000, 7 of hundreds, 4 of tens, and then 2 of ones. Really obvious stuff. It's the last step that is the most important part, because the last step here is expressing everything as the number of powers of 10 in this particular number. And that's how we read numbers. That really is. So with a binary number, it works exactly the same way. So if we look at a base 2 number, because of the suffix 2, it is a base 2 number. If we look at 101, 110 in base 2, it's broken up into 100,000 plus 00000, 5 zeros to represent that we have 0 of this particular unit, and so on. And if you keep expanding it, at some point it becomes 1 times 2 to the power of 5 plus 0 times 2 to the power of 4, and so on. In other words, we are also just specifying how many of each power of 2 do we want to have in this particular number. It's the same principle as the base 10 number. There's no changes whatsoever, no tricks. Are we still doing okay so far with the base 2 representation concept? Good? So the next slide talks about how do we add numbers in base 2. Well, before we talk about base 2, let's talk about base 10 again, because I want to make sure that we can relate everything to something that you know already. What is 6 plus 7?
13.
Okay, one way to say is 13, and the other way to say is 3 with a carry of 1. Now, the way that I just said it, 6 plus 7 is 3 with a carry of 1, makes it possible to add multi-digit numbers, right? Okay, but how do you know 6 plus 7 is 13? You cannot tell me because you have it memorized. I'm not kidding. Think about it. You cannot tell me because this is something that you have already memorized. And when did you memorize this?
First grade.
First, second grade or so, okay, depending on where you have your school. And by now, you don't even need to think about it. You look at 6 plus 7, you know it is 13. Yep.
So I don't know how you process it in your head. If you go with the bigger numbers, you can do them in your head as long as you have process them.
I use a calculator. I only have to understand enough so I can program something to do the mundane stuff. Yep, go ahead.
I was just gonna say, I mean, it really boils down to the question of we had 12 fingers when we started on consideration.
Right. Unfortunately, we have 10, so that's a really unfortunate base. If we had 16 fingers, I would like it. If we have 8 fingers even, that would be nice too. So Octopi have it easy, because they have 8 limbs exactly. So, okay, so this is a table, okay? Because in your mind, you have a table already that maps, all the possible single-digit addition to the result plus, whether there's a carry or not. That stuff you have memorized years and years ago. Is that making any sense? Okay. But what exactly is this carry? Okay. So if we go back to elementary school, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good. So you start with 6. So 6 will be here, and then we want 7, which extends out here. So the value that we are representing is out of the range of the values that we can represent using 1 digit. So that's why we have to say, oh, there's a carry because we are using up this entire block already. And then beyond that, we need 3 more slots to represent this value. That's the whole meaning of carry, okay? Because we can no longer use a single digit to represent the value. So we need a carry so that the next digit can represent the remaining portion of the value. Is that making any sense so far? Let's think about binary addition. In binary addition, okay, I'm just using my notes here on the screen. 0 plus 0 is 0. Do I need to explain that? But remember, now it's in base 2. Does the meaning of 0 change when it's in base 2 instead of base 10?
No.
Nope. Okay, that makes it easy.
Going base.
How about the meaning of 1? Does that change depending on the base?
No.
Okay, well, that makes it kind of easy because 0 plus 1 equals 1 and 1 plus 0 equals 1. Those are easily comprehended, okay? Understood. We don't have a problem with those things. The only one that we might have a problem with is 1 plus 1 is 1, 0 in base 2. Well, does that make any sense? Well, 1 plus 1 is exactly 2 in base 10. But you cannot represent the value of 2 using base 2 using only 1 digit. So you have to carry and move it up to the next power to represent the value of 2. Is that okay so far? Okay. That's the only one that's tricky. The other way to look at this is to say 1 plus 1 in base 2 is 0 with a carry. It's just like 5 plus 5 in base 10 is 0 with a carry of 1 to the next decimal place. So in this case, it is 1 plus 1 is 0, but with a carry to the next not decimal place anymore, the next binary place. And that's it. It's exactly the same principle. Are we still doing okay so far with the rules of addition in base 2? Okay. So now that we know how to deal with a carry, let's see if we can do some multi-digit addition. Before we do any multi-digit addition in base 2, let's do one in base 10 first, just to refresh our memory of doing addition by hand, right? Some of you might have forgotten how to do it. Okay, so 238 plus 195. Okay, so how do we do this addition here? 433. You have to start with which side of the numbers? The right-hand side, which is also known as the least significant side, right? Okay. So we start with the least significant digits. 8 plus 5 is 3 with a carry of 1. Any questions about that? Okay. Well, I'm asking because this is the kind of stuff that we are taking for granted because it's all memorized. We don't question that anymore. Okay, and that's why we kind of have to question it because we have to extend the same logic to binary numbers next. 3 plus 9 is 2 with a carry. And then what do we do with that 2? We have to add it to the carry from the less significant digit, which is 1. So 2 plus 1 is 3, so we have a 3 here. Is that making any sense? 2 plus 1 is 3, but we also have to add the carry from the previous digit. So we have 2 plus 1, which is 4. So the result is 433. That's okay? All right. So let's try to do the same thing with binary numbers. Now in my notes, I have one example, and the representation is a little bit different from here, because what I do is instead of doing everything kind of in a more compact form, I'm expanding everything. In other words, there are 2 additions involved here. If I do this part in that format, it becomes 238 plus 195. Okay. The first row, right under the numbers, is just representing the values that we look at. Okay. So 8 plus 5 is 3 with a carry. I use one entire row to represent the carry from the previous digit. Is that okay? Now this is all base 10 so far. This has to be a 0 because it is the least significant digit already. Nobody is going to contribute a carry to this particular column. 3 plus 9 is 2 with a carry. And then we have 2 plus 1 is 3 with no carry. Are we doing okay so far with this? So now you say 3 plus 0, because there's no carry from the previous digit, it's already the least significant digit, is 3. 2 plus 1 is 3. 3 plus 1 is 4. And we get to the same result. Okay? In other words, it's really the same thing as the shorthand version, except I use one entire row to represent the carry so that it becomes just 2 simple additions. Instead of having to take care of the carry kind of as a hidden addition, I make it explicit. Are we doing okay so far? Okay. So now we can move on to the binary example in the notes. Okay. This 0 is given because that's already the least significant digit column. Nobody is going to contribute a carry to this particular column. That's why it's a 0 to begin with. So the next step is to say 1 plus 1 is 0 with a carry. How do we know that? Well, there are only 4 rules to remember in binary addition. 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0 with a carry. That's how we know the result of this one. So you can move on like this, and then you can say 1 plus 1 is 0, and this one does have a carry. Okay. And then you move on to this one. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 0 plus 1 is a 1. 1 plus 1 is a 0 with a carry. So there are 2 ways you can contribute a carry in this case. The first one you can do, the first way you can contribute the carry is from the numbers that you're adding. The second way is from the sum of the number that you're adding and the carry from the previous digit. That can also contribute a carry. But only one can do the contribution. Only up to 1 can contribute a carry. There's no way you can set it up so that you have 2 both ways of contributing a carry. Are we still doing okay so far with this? Okay. So if you carry out this calculation, eventually you will come up with this particular result, and you end up with 0, 1, 1, 1, 0, 0, 1, 0 as the sum of these 2 numbers. Does anyone want to double check? Do you trust me? For those of you who took cisp310 from me, what do I usually say in my class? Don't trust me, right? Okay, so let's go ahead and double check. Now the way I'm going to double check this is not to do it by calculator. Instead, what I'll do is I'm going to convert the numbers to base 10 first, do the base 10 addition, and see if the result, when converted to base 10, matches the result. So I'm doing both base conversion and verification at the same time. So let's use my mouse pad here as my whiteboard, and we'll do some conversions. Okay, the first number is 0, 0, 1, 0, 0, 0, oops, 1, 1, 1 in base 2. So that means we have 0, 1, 2. Okay, let's move from the least significant digit here. We have 1 of 1 plus 1 of 2 plus 1 of 4 plus 0 of 8. The 8 is specified by this digit here. 0 of 16, 1 of 32, 0 of 64, and 0 of 128. Is that okay? Does everybody understand how to read a binary number so that we can relate it to basically base 10 numbers? Okay. And then you just add up the numbers. The 0 items are listed here explicitly just because I want to show you guys what to do with these zeros here. So we have 1 plus 2 plus 4 plus 32, and that turns out to be 39. Okay, is that 39? Okay, and then the second number, which is this one here, is 0, 1, 0, 0, 1, 0, 1, 1 in base 2. And that, I'm just going to do it really quick here. So it's 1 plus 2, no 4, 1, 8, no 16, no 32, that's a 64. And that becomes 75. Thank you. All right, so let's look at the sum. I'm not going to do the addition in base 10 yet. I'll do the addition first in base. I'll do the base conversion first of the sum represented in base 2, and then we'll double check that. So the sum, according to the binary addition, is 0, 1, 1, 1, 0, 0, 1, 0 in base 2. So that means we have a 2, we have a 16, a 32, and a 64. So if you add up those numbers, we have 80, 112, 114, I think. That's correct. Okay, so the question now is, when you do the base 10 addition, do we get 114 when you add 39 to 75? Yep, we do. So I have just double checked my calculations and not used the same route of doing the calculation, because if I use the same route, I can make exactly the same mistake and end up with the same result. This is entirely different. Base conversion first, and then base 10 addition. Is that making any sense so far? Okay. Are there any questions? I'm going to pause a little bit here and see if anyone has any question about everything that we have talked about so far. Because the next slide, we're going to do something based on this. So we got to make sure that this is all done. Yep.
So when so from here now we have 114, right?
We have 114, yes, as a base 10 number.
So it's like we just do the
39 plus 75 is 114. All right. So if there are no questions, we're going to move forward and talk about subtraction. Okay, subtraction is kind of the same thing. We'll start with base 10 first. In base 10, if I have, I don't know, let's try 2 minus 5 here. Okay, what is 2 minus 5? Well, it's -3, but it can also be represented as 7 with a borrow. Because that's the one way we can look at this, so we can chain, we can carry out multi-digit subtraction. Are we doing okay so far with this? So instead of having addition and carry, we now have subtraction and borrow. But these two concepts are pretty much the same thing. Okay, it's pretty much the same thing. The way we know that 2 minus 5 is 7 with the borrow is simply because we have memorized all of these rules already. Okay? So in base 2, how do we deal with this sort of thing? How do we deal with the subtraction rules? Let's talk about the easy ones first. 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 0 is 1. Any questions about those three? The meaning of 0 and 1 do not change depending on your base. Okay? They still represent exactly the same thing, 0 and 1. So those three are pretty easy to deal with. So the next question is, what is 0 minus 1? Well, 0 minus 1, hey, that's not enough for me to give. I got nothing, and somebody needs 1 of something. So I don't have anything. So what I'll do is I'm going to borrow from the next digit, which is representing the value of 2. So it becomes 1 with a borrow from the next digit. Pretty much the same way as a borrow in the case of 2 minus 5 to the base 10 equals 70 with a borrow. Are we still doing this okay so far? So it's the same concept as a carry in the context of addition. It's just flipped. Okay? So we can now carry out binary subtraction pretty much the same way. This is just the reverse of the previous slide, I think. Let's take a look at the numbers. Yep. It's just reversing the operation from the previous slide. I encourage you guys to do it by hand first, okay, to make sure that you come up with the same numbers. In a test, if I ask you about binary addition or subtraction, I don't care about the final result because I know you have calculators that can do it. What I care is the intermediate results, which your calculator cannot give you unless you program it. Okay? Is that making any sense? So that means I will give you 2 numbers to subtract or add. I don't really read so much of the final result because I know you can do this with a calculator. What I want to know are these 2 intermediate rows of numbers. Any questions about this? No questions? I might even ask you questions about base 3 subtraction. Would that be a difficult one, base 3 subtraction? Can we extend what we have gone over here, which is base 10 and base 2? Can we extend that same reasoning to base 3?
Sure.
0 minus 1 in base 3 is what? 2 with a borrow. Okay? 1 minus 2 in base 3 is what? 2 with a borrow. Okay? So it's the same reason. It's the same reasoning. Okay, let me just kind of show you why 1 in base 3 minus 2 in base 3 is 2 with a borrow. Because this borrow is borrowing from what? What is the value it's borrowing from? The next digit, which is 3 to the power of 1, which is 3. So we have 3 plus 1, which is 4. 4 minus 2 is exactly 2. It's the same reasoning as borrowing in any base, in base 10, base 2. Okay. Are there any questions about the basic concept of borrowing? Yep.
Could you do this again?
Absolutely. So this is all expressed in base 2, excuse me, in base 3. 1, there's not enough here to give somebody. Okay, somebody asked me for 2 of something, I only have 1 of those. Okay, and I'm 1 digit in the multi-column subtraction. So I'm going to say, okay, let's say you want 2 of something and I only got 1 of those. Okay, so I'm going to say I don't have enough to give you 2, but what I'll do is what most people would do. I'm going to borrow. Right? Who am I going to borrow from? My neighbor here. Okay, my imaginary neighbor here. Now that neighbor is not imaginary anymore, and the neighbor says, okay, I deal with numbers of 3s. Okay, I deal with 3s. You want something? Okay, I'll borrow you 1 of my stuff, which is a 3. So now back to here, I say, okay, I have 1 to start with, and I'm borrowing 3 from my neighbor. So now I have 4 of something. You want 2 of those? Okay, I'll give you 2. And I will have 2 remaining. And that's why we have the 2 here, and also a borrow, because I did not have enough to begin with. That's why I have to borrow from my neighbor. Yep. You can always borrow from something. 31 subtracted by 32. Okay. That's a good question. Okay, let me write it out in mousepad here so it can be captured. Okay, so the question is, what if there's nothing to borrow from, like 31 minus 32? Okay, that seems to be a good question. It is a good question. Okay, so this one is always a 0 because it is already the least significant column, so there's no borrow generated from there. All right, So 1 minus 2 is 9 with a borrow. Any questions about that? Okay, so we'll put a 9 here, and we'll put a borrow here. Is that okay so far? Okay, same concept that we have been talking about. 9 minus 0 is 9. Okay, we'll put a 9 here. Okay, cool. 3 minus 0 is, excuse me, 3 minus 3 is 0. It does not generate a borrow. 0 minus 1 is 9 with a borrow. In other words, we end up with a borrow from the 100. And that's the end result. Okay? Now, you can look at this two ways. You can look at it from exactly this perspective and say 31 in base 10 minus 32 all in base 10 is 99 with a borrow from 100. But you can also look at it from the perspective of it is 99 minus 100 because you have to account for the last borrow. 99 minus 100 is negative 1, which is exactly what most people would have expected from this subtraction. Is that okay? Okay, that was a good question. I really like that question because it kind of lead us to the remaining borrow, okay, that is kind of dangling out there. In a computer, when you do subtraction and addition, you also potentially end up with a dangling carry or dangling borrow, and that has significance later on in this semester. So that's a very good question. It connects to something that we will talk about later. All right, so that is done. So let's move on to, where's my stuff? I think it's in the other browser. All right. So moving on, it's already down to the summary. It's basically pretty easy, right? Okay, binary subtraction and binary addition is actually easier than we think it is. Are there any questions at this point about binary conversion and binary addition and subtraction? What about binary multiplication? I mean, how do we multiply binary numbers? Does anyone want to give it a try? Okay, I'll give you an example. Okay, so let's use an example here. If you know how to do, okay, technically speaking, if you know how to do addition, you already know how to do multiplication because you can just add the same number many, many times. But nobody's going to do that. Okay, we have tricks to do it, right? Okay, so let's take a look at two binary numbers, and we want to do the multiplication here. So let's say we have, 1, 0, 1, 1 times, let's try 0, 1, 0, 1. Okay, that's my multiplication in base 2. Base 2. In base 2. Okay, so how do we deal with this? Well, we use exactly the same technique as in base 10 when it comes to shifting the numbers by the digits. The only part that is different is when we do the addition between the rows. That's the only part that is different. So that means in this case, we'll end up with 0 of 1, 0, 1, 1, but it will be shifted this way. So we will say, we have 0 of this, and I'll just go ahead and pad the zeros. Is that making any sense? No? This 0 comes from this 0 here. These 3 zeros, the padding zeros, comes from the fact that we are handling this particular place times that, which is kind of the same way you do base 10 multiplication, except with just dealing with base 2 numbers. Is that okay? The next one is 1 of 0, 1, 0, 1, 1, 0, 0. This is just a leading 0. You can ignore that if you want to. This 1 comes from this number here. 1, 0, 1, 1 comes from here. And then the 2 padding zeros at the least significant side comes from these 2 digits. And then we also want to add 0 of 1, 0, 1, 1, 0. I'm making this very explicit, just so that we can see the pattern, okay? And then finally we have 1 of exactly 1, 0, 1, 1. And that comes, this 1 contributes to this 1 here. 1, 0, 1, 1 contributes to this part here. But because this is already our unit, we don't have any least significant digits to pad anymore. So now your only remaining task to do is to add up these 4 numbers. Now, fortunately, 2 of these boil down to zeros. So if I really want to do the addition, it becomes 0, 1, 0, 1, 1, 0, 0, 0, plus 1, 0, 1, 1. And the end result, this one is pretty easy. It's, I'll do it the right way. So this is 1, 1, 0. This is 0 with a carry. So the carry goes to this part here. It becomes 1 plus 1 also. So the result is 0 with a carry. And that one is just 1 here. So that becomes the end result. Let's double check and make sure that the calculation, in fact, is correct. 1011 in base 2 is what value? How do we represent that value in base 10? It's 8 plus 2 plus 1, which is 11, okay? In base 10, so I'm going to make this explicit here. What is 0101? It's basically 4 plus 1, which is 5, okay? 11 times 5 is 55. So we want to check to see if this number is representing 55. So we have 1 plus 2, no 4, no 6, no 4, no 8, no 16. There's a 32, and okay, I messed up somewhere.
Which one of those zeros?
You need a
1, 0,
4.
0, 1, 0, 1, 1, 0, 0.
Yeah, it should be two zeros instead of 3 zeros when you're adding together.
You're just a
Addition. Count it, one more.
This part here?
Up one.
Just up.
Down
What?
one. Down. Yeah.
Down. 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 There, right. Up.
That way.
There you go.
You only need 2 zeros.
Oh, okay, I see. So it should be like this. Dope. Okay, thank you. So 1, 1, 1. This is still a 0. This is a 1.
No, you missed a 1.
That's a 1,
Yeah.
2. That's a 0. That's a carry to the next one. And then this one is just 1. Okay. 1, 4, no 8. There's a 16 and a 32. And 7 plus 16 is 23. 23 plus 33 is 55. So we got our result back. Sorry about the mistake.
I was just checking to see if you guys were
Sure you were.
Sure. But good catch. I mean, those of you who caught it, it's like, wow, good job. Okay, so it doesn't work out. What does the multiplication table look like in base 2?
2 by 2.
You only have 4 entries, right? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. That's your entire multiplication table. Why did we have to spend all that time to memorize the base 10 multiplication table? That's just silly.
Most people aren't as nerdy as us.
That is just silly. How long did we spend to memorize the base 10 multiplication table? The entire 3rd grade, almost. Right? And here we know we could have done base 2 and be done with it in a day. All right. So this is already done, okay? So we are done with binary addition and subtraction. However, there's more to this stuff. Okay, so what I'll do is I'm changing the order. I'm gonna change the way it's reflected in Moodle as well. So I'm gonna change the order here and move this stuff here up a little bit. Okay, I'm just trying to find out where I put that. Half adding and full adding, I think that's it. Okay, so we're gonna deal with this next. And the first part of this, deals with, addition. Okay, let's go back a little bit. Let's go back to my mouse pad here, and we'll revisit addition in base 2. Okay, so let's go ahead and revisit, addition in base 2. let's start with 0. 0 plus 0 is 0 with a carry of, well, it doesn't have a carry, but you can also say it has a carry of 0. Okay, it just doesn't contribute anything to the next digit. 1 plus 0 is 1 with a carry of 0. 0 plus 1 is 1 with a carry of 0. The only one that is a little bit tricky is 1 plus 1 in base 2, which is the result of 0 with a carry of 1. Okay. So we look at these 4 rules. Let's see if there are any questions about these 4 rules. We're just recasting it a little bit differently here. Is that okay so far? Okay. The input is the left-hand side. In other words, the input in this case would be 0 and 0 as the input, and I want the output to be a 0 for the result, and I want a 0 for a carry. Am I doing okay so far? Because I'm trying to okay, let me tell you what I'm trying to do. I'm trying to translate the calculations that we did here into logic gates and transistors. That's what I'm trying to do. Okay. How many people already know what a logic gate is or what logical operators are? Okay. What is a logical operator in C? Give me an example of a C logical operator.
Or not.
And or not. Very good. So how do you write the AND operator as a logical operator in C++ or C? 2 ampersands. Very good. Okay, not 1, but 2 ampersands. Okay. So for those of you who may have forgotten this or have not encountered this in your previous classes, basically 1 and 1 is 1. 0 and 1 is 0 because false and true is false. 1 and 0 is 0 because true and false is false. 0 and false, 0 and 0 is 0 because false and false is also false. Are we doing okay so far with that? Or some of you may not have any exposure to it. If you have not exposed to the ampersand operator, you have to let me know because I have to explain that. Okay, is that okay with everybody? Okay. And likewise, we have the logical OR operator, right? The logical OR operator is represented by 2 vertical bars. 1 or 1, which is true or true, is true. True or false is true. False or true is true. And then we have false or false is false. And technically speaking, since I'm using C++ operators, I really should use the comparison operator here, because otherwise it becomes an assignment, which is not correct in this context. Okay.
You missed one.
Oh. Okay. So those are the 2 basic operators, and then we have a third one, which is really useful. It is the negation operator, right? The negation operator is a single exclamation point for logical operators. Not true is false. Not false is true. Okay, so we got all 3 basic operators here. What we want to do is to say, instead of using addition, is there another way to come up with the answers here? In other words, I give you the 2 inputs here. You come up with a logical expression that come up with that column as the sum, and you come up with another logical expression to come up with the carry. That's the question. We have the inputs defined to be these 2 columns. We want the output, one output to be this column. We want another output to be that column. So the question is, how do we do this? How do we use logical operators to perform arithmetic addition? That's the question. Now, before we do all the detailed stuff, the chore stuff, let's think about why is it significant? Why do we want to do that? Why do we want to define addition in terms of logical expressions? Because we want those to be performed by computers, and computers internally have what?
On and off switches.
We use we use the transistors in that particular way, it's either on or off, and we have logic gates. Okay, we can implement logic gates that are equivalent to the ampersand, ampersand, and or operators, and also the negation operators. So we want to translate addition into silicon. That's what we want to do, because that's how you're going to design a processor on the inside of the processor to perform addition, subtraction, and all the other basic calculations that you want to perform. Am I doing okay so far? Do you guys understand why we are interested in converting arithmetic addition to logical operations? Okay, so now that we understand that, the importance to do that, let's go ahead and use some symbols here. So in other words, instead of just referring to the first, second, and third, and fourth column, let's call this input A as a symbol. This is input B as a symbol. This is our sum, and this is our carry. Okay? And I want basically a way to describe sum as some equation, some expression involving A and B. I want to define the carry as an expression that involves A and B only. Okay? That's your exercise. How can we do something like that? Let's deal with the easy one first, okay? Because the carry is the really easy one. Okay, if you look at the carry column, which is the rightmost column, and then column A and column B, and you look at the logical operators that is already on the board, which one will do it right away? Ampersand, ampersand, ampersand. Logical operator can compute the carry of a addition operation natively. There's no need to do anything else. You just say the carry is basically A and B, or if you want to express it in the usual logic way, it is also known as A and B. But for those of you who eventually will get into computer engineering, the way to express this is simply the product of A and B. That's one way to express conjunction. Conjunction is quote-unquote multiplication. Are we doing okay so far with this? Just, representation of conjunction, or and, as we call it in programming. Okay? The sum, the third column, is a little bit more tricky. We don't have any single operator that can do this trick. But we can combine stuff, can't we? Okay? So what we do is we can now combine A and B in different ways, and then combine the sub-expressions into the bigger expressions. So what we'll do is we'll say not A and let's see, not A and B, or not A and not B. Okay? And I'm still using C compatible operators here. The first version is just using operators that we are supposed to know already, because these should have been introduced in your C++ class. Okay. Well, hold on a second here. You guys should not trust me, right? So we better make sure that that expression, not A and B, or A and not B, would actually come up with the column 0, 1, 1, 0 when the input are the columns A and B. Let's double check. Make sure that it really is the case. Okay. So what we'll do is we will define A and B, and then we'll come up with not A and B, or A and not B. Okay. Now A is a Boolean. It's a Boolean variable, so it can have values of zeros and ones. B is independent to A, so that means when A is false, B can be false or true. When A is true, B can also be false or true. Those are the four possible combinations when you only have two independent Boolean variables. Is that okay so far? Because I can enumerate all possible combinations when it comes to Boolean expressions. Is that okay? So those are the inputs. Those are the only four possible inputs to this particular equation or expression. So now I want to compute the actual result here. Okay? If you want to do it step by step, I can go ahead and do it step by step, but I will have to erase certain parts of this. So if A is 0, not A is 1, and then B is already 0, so B is 0 here. 1 and 0, or true and false, is the whole thing is false. And then on the other side, we have basically the same thing, because it is just symmetric. A is 0, so we have 0 here. B is 0, but not B is going to be a 1. 0 and 1, the whole thing becomes a 0. So now we boil down the whole expression to 0 or 0, which is 0. Okay, very good. Okay, so let's look at the second row here. We have A being 0, not A becomes 1. B is already 1 for this particular row. 1 and 1 is 1. Okay, and then we look at the other side of the OR. A is 0, B is 1, not B is 0. 0 and 0 is 0. So now the entire expression becomes 1 or 0. What is 1 or 0? 1. The whole thing just becomes 1. Very good. As you can see, this is symmetric. Okay, the next row is symmetric because instead of having A being 0, B being 1, we have A being 1, B being 0, and because conjunction and disjunction are both symmetric, they are commutable. Okay, so that means we're gonna get exactly the same result of a 1. The only other one that we actually have to work out is the last row. Not A. A is 1, not A is 0. B is a 1, 1 and 0 and 1 is a 0. So this entire side becomes just 0. Let's move on to the other side. A is 1, B is 1 as well. So it becomes 1 and 0. 1 and 0 is 0. So now we have 0 or 0, which is also 0. Are we doing okay so far with the calculations? Unfortunately, because the way I'm doing it, I have to kind of erase it. But the good thing is it's also getting recorded. So if you have any questions about this step, you can kind of watch the video and kind of slow motion this part. Take screenshots, right? Take lots of screenshots in slow motion. Okay. What have we just accomplished? We just proved, right? We just proved that this expression is the same thing. It will calculate the sum of 2 bits. Great. So now we can just say, oh, okay, that's verified as well. So I want to give you the alternative expression to this. Some of this I cannot express it here. It becomes not A times B plus A times not B. Okay, that's one way to express it. When you are actually doing this as a computer engineer or an electrical engineer, the not is usually done by an overbar. So you would see a bar on top of A for the first part and a bar on top of B for the second part. Addition in a Boolean expression means disjunction, or. That's the convention. That's the convention in electrical engineering as well as computer engineering, so that we don't use or and not those words. Are we still doing okay so far with these concepts? So what we have done so far is to express the basic rules of binary addition in terms of logical operations. Okay? And the result is significant because we already know how to implement an AND gate. We know how to implement an OR gate. We also know how to implement a negation inversion gate. So that means if I know the equation, I can actually use 74 logic, 7400 series logic gates, and use a breadboard and wire it up and do it in hardware. Okay? Because you can buy what we call jelly bean parts. The 74 parts are called jelly bean parts because they can be used. Well, first of all, there's a great variety of those things, and two, they're also very inexpensive. So that's why they're also referred to as jelly bean parts. And so we can basically get a breadboard, plug in a few of those parts. One part to implement AND gate, one part to implement OR gate, one part to implement NOT gate, wire it up, and actually have the input coming in with A and B, and have the output being the sum and the carry. Okay? And the significance is now we can do it in hardware. Are there any questions up to this point with this part of addition? Well, this is called a half adder because it's only one part of addition. So let me show you why it is called a half adder. So let's deal with only a 2-digit addition. Go ahead.
So what was showed right there, on the top right there, was the AND gate or what was it? Like a
Which part of it?
0110. What is it? Like the answer you got there, 0110. What is they representing right now? What gate or what logic are they representing right now?
Say again?
0110.
It's addition.
The sum.
Is simple addition?
You mean this part here?
No, the 0110.
The 0110.
The sum.
Yeah.
You mean this part here?
Yeah.
That's the sum of the output of a half adder. It's based on the rules of addition in binary. 0 plus 0 is a 0. 1 plus 0 is a 1. 0 plus 1 is a 1. But 1 plus 1 is once again a 0 because we have a carry to specify the other part of the result.
And that's what the half addition is.
And that's why it's a half adder, because it has not taken account of the carry part. So when you read my notes, it looks like this, okay? Instead of A and B, I use XY. Instead of sum, I use result. But basically the same thing, exactly the same thing. And it is also expressed like this. The prime here, or the apostrophe, is the representation of the negation of the symbol right before that. So that's another way to represent negation. It means negation of the one before.
So it looks like a product group.
Product group? Oh, okay. Not related. Okay. So are there any questions about this slide? It's really just a recap of exactly the same concept, except I label the columns a little bit different. Okay. So now that we know what a half adder is, let's take a look at what a full adder is. The full adder, okay, well, you can read the slide, but I can kind of show you what it is, actually on the board, or yeah, let's do it on the board. Okay, so let's just pretend that we are adding two-digit numbers. Okay, just two two-digit numbers. So the first number is A1, A0. Okay, A1 represents the most significant bit of the first number. A0 represents the least significant bit of the second number. Then we have B1 and B0 here. Well, I better do it on the notepad just so that it is captured. So that when people ask me again, I will say, well, you can watch the video again. Okay, so we have A1 being the most significant bit of the first number, A0 representing the least significant bit of the first number. And we want to do an addition to B1 and then B0. Okay. So according to our equation, okay, let me just make this a little bit more spaced out here. This is the result. Okay, so using our representation, this becomes the result of A0, B0. And I'm going to need a little bit more space. Like so. And then this bit here is always going to be a 0 because it is the carry from a non-existent digit. Okay, are we doing okay so far? In other words, I'm trying to represent the same thing that we have been talking about, but this time I'm just using a particular symbol to represent a bit, the position of a bit, and then use the R and the C as defined a little bit earlier. And this result here, down here, because we're just adding 0, there's nothing really special about it. It's just that. Okay. But this one is a little bit more special because this part here is still going to be our A1, B1. Okay. Is that okay?
Not the one.
Oh, B1. Okay, there we go. And we need to space out one more. What about this part here? What should we write here? What is going to be in that place? Is the carry of the addition of the prior column. Okay, now that gets tricky. Yep, go ahead. Multiplication. Right, exactly. Well, that's one of the contributors, okay, but not the only. Well, in this case, it is the only one because the other one is going to be a 0. So it is the carry from adding A0 to B0. Okay. So how do we express this part here? I'll just call that, let's call this x here, because I don't have enough space to express x. X is what? X is the sum of two things. Which two things are we talking about?
This one and the carry.
Sum of this and that. Are we making any sense so far? Kind of? Okay, when you look at the picture, and I'm pretty sure I have one somewhere. Maybe not. Maybe it's in another slide, so I'm going to talk about that next time. We are running out of time today. So what you want to carry away from today is the half adder concept. And then next time we'll talk about how we attach two half adders to become one full adder, to take care of one column completely when we're dealing with binary addition. Okay? But you have to kind of study a little bit, because if you're not familiar with these concepts, it's hard to kind of go over these slides one more time just to make sure that you know what I'm talking about. Okay? And then plus you have your homework assignment, which is nothing except just following some steps to make sure you know how to play your homework assignment. All right. Have a nice weekend, and once again, Happy New Year. Year of the Horse.